now we can figure out the maximum force. The force as a function of time is no longer on the board. No, there it is. It is negative 3.034 times 10 to the 6th t squared plus 1.91 times 10 to the 4th t. In order to figure out the maximum force, that's going to be the force at 0.00314 seconds, which equals negative 3.034 times 10 to the 6th t squared, where the time is 0.003141 squared plus 1.91 times 10 to the 4th times 0.003141. Please tell me what the maximum force is. What do we get? 29.85 newtons. Notice, this is right about there, which is actually slightly less than our actual data point because we've actually taken a best fit curve, which if you look doesn't quite make it all the way up there. So this is an approximation. Remember that. We've got the maximum force. Good. We're now going to figure out the velocity as a function of time. How are we going to figure out the velocity as a function of time? We're going to integrate the acceleration, the integral of the acceleration as a function of time. We have the acceleration. Somebody give me the acceleration. Tyler, you got it.
Wait, what?
I need the acceleration. I just erased it.
I got it somewhere. Hang on. Oh, found it. Okay. Negative 7.506 times 10 to the 7th t squared plus 4.716 times 10 to the 5th t.
Independent confirmation of that acceleration? Great. It is?
Yeah.
Oh, there it is. I'm sorry about that. So we have then the acceleration is just the integral of this, which is going to be negative 7.506 times 10 to the 7th t cubed over 3 plus 4.716 times 10 to the 5th t squared over 2 plus c. Let's figure out the plus c in a minute. Help me first out by dividing these by 3 and 2 so we get numbers for this. Remember, this is an indefinite integral, so we don't have limits on this. We need to figure out the initial condition. Hold on, just a second.
Negative 2.5 times 10 to the 7 plus 2.358 times 10 to the 5.
Okay, we still have our plus c 2.5. We have a little bit more here.
Oh, 2.
0.2. Okay. Now, plus c. We have an issue here that we don't know the initial condition. How are we going to figure out the initial condition? Okay. We could, but we don't. We're not going to. That actually would be assuming that I dropped it from the correct height, which is not a very good measurement. There's a way to figure this out. It's not always solving for the initial condition. We could solve for c given that we know something about the velocity. We know the velocity at a certain point. No, we don't know the initial velocity. That's what we're trying to solve for. Where do we know the velocity? De Silva.
The max force when it's stopped.
We know the velocity when it has its maximum force. De Silva, what is it? What's the max force? What's the velocity at that point? 0. So we know the velocity at time t equals, where'd it go? 0.003141 is equal to 0. So we know negative 2.502 times 10 to the 7th t cubed, or actually let's plug in our numbers here, of 0.003141 cubed plus 2.358 times 10 to the 5th times 0.003141 squared plus c. And we can solve for c then. What do we get for the velocity initial, which equals c, which is equal to? What do we get?
Negative
1.55 is plenty there. So 1.55 meters, or actually one more, 1.55.
Oh, okay, no, negative 1.55 positive. This is so equal to 0, so oh wait, yeah, no. So negative. Or wait, never mind.
Negative 1.55.
1.
Negative, of course, because it's going down, which means we have figured out the velocity as a function of time is equal to negative 2.502 times 10 to the 7th t cubed plus 2.358 times 10 to the 5th t squared minus 1.551. Don't you worry, we can also figure out the position as a function of time. Please tell me, oh yeah, I love it. Please tell me, Catherine, how we're going to figure out the position as a function of time.
By integrating the velocity.
We know the position as a function of time is going to be equal to the integral of the velocity as a function of time. We have the velocity. It's negative 2.502 times 10 to the 7th t cubed. With me, people, 2.358 times 10 to the 5th t squared minus 1.551. Taking the integral with respect to time, we get negative 2.502 times 10 to the 7th t to the 4th power divided by 4 plus 2.358 times 10 to the 5th t cubed over 3 minus 1.551 t plus c. 2.502 times 10 to the 7th divided by 4, please.
6.255
Times 10 to the
1.
6th.
Yes, 6.
Plus
7.86 times 10 to the 4th.
t cubed minus 1.551 t plus. Now, c is the initial position. And we're just going to let x initial equal to 0 because it doesn't really matter. It's just position relative to what? So our initial position we're going to say is equal to 0. Okay. I will not do it, but we could plug in the time to figure out the maximum position. We're not going to do that. That will give us the maximum compression. I am, however, going to do this. We come back over here. We come back to the data. We have the position as a function of time. We'll do the position as a function of time in meters. We know that is equal to, here we go, negative 6.25500, is that correct? 1, 2, 3, nope, one more, times the time quantity to the 4th power plus 7.8612, yep, times 10 to the 4th, times the time to the 3rd power minus 1.551 times t. This is our position as a function of time. Now, what we're going to graph is we're going to graph force as a function of position. This is on the x-axis we have the, that doesn't really matter. On the x-axis we have the force in newtons, so it's actually position as a function of force, but it doesn't really matter. And the position on the y-axis. We don't need a legend. This is technically the position versus the force, and you get this, and we can add a best fit line, and you can see that it is actually a best fit line with a y-intercept of 0. We can change this so that we can see the scientific notation. We have the font going to size 28, and you can see this. No, not yet. Actually, I want to change. Just a second. I don't like this. I got to change. I'm changing my x and y so that we have the force as a function of position, which is going to be much better. There we go. Force as a function of position. I feel better. Okay. So here's the thing. The question is, what did we just figure out? We just figured out that the force graphed with respect to the position of the racquetball is linear. Tim, what did we just figure out?
The spring constant of the ball.
We just figured out the spring constant of the racquetball. Ladies and gentlemen, given the force as a function of position, we were able to figure out the average force, the impulse, the maximum force. The force is a function of time, the acceleration is a function of time, the maximum acceleration, the position is a function of time, the velocity is a function of time, the total time for the impact, the time at which, and the spring constant of the racquetball. Think about that.
Wow. Our next.
The spring constant, well, we graphed the force as a function of position. F equals negative kx. The spring constant right there is 1.02 times 10 to the 4th newtons per meter. Ladies and gentlemen, I hope you enjoyed my demo.